So welcome everyone. Before we get started, I would like to ask you to raise your hand if you've ever felt like an underpowered engine struggling up a hill when dealing with performance issues in Angular apps. Oh, I don't see a lot of hands as I have expected. But anyway, so today we are going to shift gears and hopefully we'll put an end to that. Before diving into the nitty-gritty details, I would like to tell you a little story. So this was me, actually, on October 21st, 2019. I was explaining my feeling to my team after getting the following result about the Angular app I have implemented most part of. And on the bottom, that was my colleague who was working on another Angular app, laughing at me because his app had a better performance. But that's not what we are going to talk about today, because at that time, my Angular app was suffering from a terrible loading performance, and today our focus is on render performance. As you can see here, it took over 41 seconds to load the page on the browser. So before checking what you should do in order to avoid ending up crying just like me 4 years ago, let me introduce myself. So I'm Rakia, a software engineer with 17 years of experience. And I'm a Google developer expert in Angular, and I'm also a content creator with over 140 articles on Medium. And I also share my experiences on YouTube. I have a Udemy video course about web performance and memory leaks, so feel free to check it. So when we talk about web performance, we are not referring to a single monolithic aspect. It's actually a complex tapestry that has multiple aspects and metrics that we can categorize under 3 broader types. So first we have load performance, which focuses on how quickly the resources of the page can be loaded and displayed to the user. And this is important because the quicker your page loads, the faster users can interact with it. And next, we have runtime performance. A well-optimized runtime performance ensures that your application remains responsive and efficient over time after it has loaded. It includes things like JavaScript execution speed, memory usage, and event handling. And the third piece of the puzzle is render performance. It focuses on how smoothly your page renders and refreshes, especially during interactions like animation and scrolling. Having explored the 3 pillars of web performance, let's focus now on rendering. So what exactly is this process? At its core, rendering is the process of taking your code, the JavaScript, CSS, and HTML you have written, and transforming it into something the user can see, interact with, and experience. This journey begins with parsing your code to understand the structure and styling instructions of styling instructions defined by your HTML and CSS, and also the behavior defined by your JavaScript. From that, the browser will construct the document object model, which is a tree-like representation of your HTML. Then comes layout, in which the browser will calculate where each element should be positioned and how much space it should occupy on your page. And finally, the browser paints. It fills in pixels according to the layout it computed, bringing your page to life. So let's see now a visualization of this process for this page on Mozilla Firefox. We are going to see the work done by the browser in the background in order to show us this view. It's extracted from Ryan Saddon GSConf talk 2015. So here, all the DOM nodes are converted into render objects, which have graphic information and visual outputs. And the browser is figuring out where each element and its children should be positioned on the page. And this is the final result. If you want to reproduce a similar visualization by yourself, you can go to Chrome DevTools, then click on the three dots there, then click on More Tools, then go to the render, sorry. I need to move it a bit. So on the Chrome DevTools, there is a three dots on the bottom right, and there you need to click on it, then click on More Tools. Then you can open the render panel, and we will see that we have to check two boxes in order to highlight the borders of each element so that we can visualize the render process when we reload the page. So I will start again. Yeah, here I have chosen the first one and the layout borders. The first one is the paint refreshing. After that, you can load or refresh the page as I am doing here for the Medium website. So it's a bit more quicker than the previous page. And now we are going to see the render process for my profile page on Medium. So, and that's it. So depending on how much time the browser will need to load and render the content, the browser may notice the following steps while waiting to interact with the page. First, the navigation begins. After that, the first non-blank paint will be noticed on the screen. After that, we have an important metric, which is the first contentful paint, and it reflects that the navigation has successfully started. After that, so we have first that the page's primary content will be visible on the page. Then the page will look nearly done. Then we have another important metric, which is the time to interactive, and it reflects that the content and the page is visually usable and engageable. And this will bring us to the end of load lifecycle. This journey has actually three key moments. First, whether there is something happening on the page, then whether the content is useful, and the third step is whether the content is usable. So now that we have a better understanding of what rendering is, let's check how this process can take place. Not all rendering is created equal, and different methods could have a significant impact on the user experience and the performance. So first we have server-side rendering, in which the HTML is fully loaded, fully rendered on the server and sent to the client. And in the Angular world, SSR is based on Angular Universal, a technology that allows Angular to render pages on servers, because by default, Angular render pages on the client. With SSR, apps render faster on the browser, because the user can start seeing the content while the rest of the JavaScript is still loading, which improves the perceived load time. With SSR, there is no need generally for powerful devices because most of the heavy lifting is done on the server. And SSR is also SEO friendly. Yet, although it puts actually a heavy load on the server, because each request from the clients needs a full page to render. And while it can reduce the load time, it can actually delay the time to interactive because you can see the page quickly but can't interact with it until all the JavaScript is loaded and executed. And SSR may also not work well with applications that manipulates the DOM. So next we have CSR, or client-side rendering, in which the browser downloads all the JavaScript, then uses it to create and insert the HTML into the DOM. With this approach, logic like data fetching, templating, routing are handled by the client rather than the server, which is actually great for applications that requires rich interactive features because interactions are much smoother because no round trip is needed to the server for each change, like in the case of SSR. CSR also reduces the server load because it's almost responsible for the initial payload and for handling API calls. With the CSR, you can also cache data and states on the client without involving the server. But you may notice a slower initial load time because the browser will need to load, parse, and execute all the JavaScript before it can start rendering the page. Search engine crawlers might also struggle with CSR pages, which impacts SEO. And we may notice performance issues on low end or not so powerful end devices. But that's not the end of the story because there is a third approach that seeks to combine the benefits of both SSR and CSR and create a hybrid model that offers us the best of both worlds. A web application can use SSR for the initial page load to improve the performance and the SEO, then switch to CSR for subsequent animation and interactions. So on this picture, we can see that SSR on the top was almost the standard in the old day used with the languages or frameworks like PHP, GSP, and so on. 10 years later, with the trend toward single-page applications, the trend was CSR with frameworks like Angular, React, and Ember. And now there is a new trend to combine both approaches. So as symptom of poor rendering performance, you may notice long time to interactive, sluggish responsiveness, and layout shifts. Cumulative layout shifts are actually a metric that measures how much elements on the page moves around unexpectedly. We have here a short demo about such a case. So here the user is on the order page. They see that they have 56 items. They can confirm or cancel. But as they tried to cancel and go back, there is a new item on the, or DOM element. So it was an advertisement actually that was injected in the page, which caused that the rest of the page was shifted to the bottom and the click event was triggered on the confirm, which can have some dramatic consequences depending on the case. So, and the culprit behind this could be actually inefficient JavaScript or CSS, large DOM, unoptimized images or media, too many requests to HTTP requests, lack of caching, or server performance, excessive use of web fonts, or even render blocking resources. Render blocking resources are resources that prevent the browser from rendering or displaying the page until they are fully loaded, parsed, and executed. As optimization technique, we can reduce JavaScript execution time. We can also optimize our style sheet and images. We can minimize layout thrashing. Layout thrashing occurs when JavaScript repeatedly changes the DOM and forces the browser to recalculate elements' position and dimensions, which can degrade performance, especially in complex or large DOM structures. So here we have an example in which, so there is one write operation on the top, then there is a read operation, then another write operation, then another read operation. So in this example, the browser will need to recalculate the layout after each write operation because the next read operation might be affected by the previous write. And this can cause laggy user experience, choppy animations, and slower rendering performance. So you can also leverage on push change detection, but keep in mind that you need to consider things like mutability issues in your code design when you are using it. And you can leverage progressive rendering and lazy loading. Progressive rendering improves the perceived performance, and lazy loading reduces the initial payload and the time to interactive. And with this, we come to our case study, which is a log management application. So I need to switch to the browser. Sorry, I can see the browser. Mm-hmm. Ich sehe, ach so, ja. Okay, so this is our case study. It's a log management application that displays a list of SES field sets. SES, or Elastic Common Schema, by the way, is a standardization effort made by Elastic, the company behind Elasticsearch, and it defines a common set of fields for ingesting data into Elasticsearch. So here, on this table, when the user clicks on a row, they can see the details of these field sets, including a list of SES fields displayed as ships list. By default, the first one is selected and highlighted with the blue color, allowing the user to see its details. The user can also see the details or check the details of other fields by clicking on them, as I'm doing here. And in addition, they can also click on the Show All button to display the details of all the fields for these field sets at the same time. So as I have done now. But I have noticed that displaying the details of 29 fields can take 2 seconds and get worse when when the number of fields is incremented. So I need you to show a case or an example of that. In TLS, we have 29 fields. Yeah, it's this one. And here we have 29 fields. So 1, 2, almost 2 seconds to render the details of all those fields. But let me show you another case study, which is thread. It has 60 fields. So here we have 60 fields. 1, 2, 3, 4 seconds. There is also another worst case with 111 fields. It's geo. This one. 1, 2, 3, 4, 5, 6, 7. About 7 seconds to display these details, which is, of course, not optimal for the user experience. So after seeing this problem, I will go back to TLS, the case with 60 SES fields. Then we will open DevTools in order to get some insights about the performance metric. So I will go to these 3 dots, then more tools, then I will open the performance monitor. So after that, I can click on the Open All button. And here you can see there are multiple charts. The first one displays the CPU usage. The next one displays the JavaScript size. Then we have the DOM nodes, the JavaScript event listeners. There are also other ones, and you can select or unselect each of them. So now we have all of our fields highlighted with the blue colors, which means we have all the details displayed. And as you can see, after I have clicked on the Show All button, there is a jump there on the top, which reflects how many CPU is used. There is also a jump in this chart. I think it's for the JavaScript heap size, and this is for the event listener, I think, and the DOM nodes. So next I will go to the performance timeline record in DevTools and try to get other insights from it. So I will close this one, hide all the details. Then I need to go to the performance panel. And it's recommended to click on this garbage collection button. After that, I will start recording the scenario that I will perform now. So I click on the show all. I think the click was not triggered. Yeah, okay. And I will do the same for thread with the 60 fields. Okay, now I will stop the record. It will take a moment to generate the result. Okay. So this first block is associated to the field set with the 29 fields. As you can see here, there is a lot of lila color, which reflects the rendering, how much rendering was done by the browser. It's more than the scripting. And the second one has also used more. So it has about six seconds rendering, and the rest about 2 seconds for scripting. So with this insight, it's clear that we have a rendering problem in this case. And before implementing the solution for it, I would like to go to the source code now. Okay. And here I am in the field set component in its template. Here we can see that we have two alternative DOM blocks. The first one will be displayed when only one field is selected and the open all fields variable is false. And the next one, or the second one, is displayed when open all fields is true, and it has this loop in order to show us the template for the fields and times. So if I go now to the child nested component field and then check its template, so it's a long template, and you may have noticed that we have a lot of matform fields. If I try to count them, I am in the wrong template. So I wanted to go to the template of the child. So, and okay. So here we see that we have 28 matform fields in this template, but that's actually not the whole truth, because there are also some other nested component in this template, and they have also further matform fields. But if we try to focus just on this 28 matform fields in this template, this means that when the browser needs to render the details of 29 fields, it needs to check and calculate and render over 800 matform fields. And for the thread case, which has 60 SES fields, it has to check 1,680 matform fields, which can explain why it took a lot of time to render all these details. And for the geo with the over 100 fields, it needs to check over 3,000 matform fields. So to solve this problem, I want to opt for progressive rendering based on Rex.js. I have, actually my goal is to have a solution that allows me to deliver the items delayed over time, and instead of delivering all of them at the same time. I have prepared a function here. So it's this one. Basically, it takes the array of items and then it just transforms it into an observable. Then it delivers the item by using this delay operator, and it delivers one item, then waits 1 second, and then the next items. That's nice, but I would like to have a better solution that allows me to configure this delay time and also to deliver a batch of items instead of delivering one item and then the next one. For this sake, I can use a solution presented by Giancarlo Bonfresco in this article. It has actually the base concept, the same concept, but it pipes the created observable through a lot of Rex.js operators. It uses buffer count to group the emission into subarrays, then concat map in order to map each subarrays into delayed observable by using the delay. And then it accumulates the subarrays into one array here. And lately, it checks if this is the first emission or if all the items from the array are emitted. If so, then it sets its first emission to false. Otherwise, it doesn't do anything. So now that I have my function, I need to go to the template where I get the list of all the SES fields, and the correct implementation for the solution needs to consider delivering all the ships list at the same time without lag or delay. And just after you click on the show all button, the details should be rendered progressively. So for that, I need to go to this field set component, and I want to define a variable lazy fields, which should be an observable. So it's this one. It's an observable of SES fields array, and it's initialized with an empty array. Then when the user clicks on the toggle all button, I am calling this method. There I need to change the value for these lazy fields. So here I need to transform this fields into an observable, then call pipe, then call the lazy array. May I have a few seconds? A few minutes, I mean. Okay, thanks. So I have transformed my initial array into an observable, then called the lazy array function in order to deliver the items over time. But that's not quite correct, because when the user clicks on the show all button, maybe they want to hide the details and not showing them. That's why I have to check the value of this open all fields variable. If it's true, then I will do it this way. otherwise, I will just um, give an observable of an empty array as value for that. So the last thing that we have to do is actually to change this loop. Instead of using fields, we have to use lazy fields, and then we need to call the async pipe. Okay. Now we are ready actually to go to the browser and check the result. I will close DevTools. Okay. We need to go to thread with the 60 fields. And check how much delay we will have now. So as you can see, there is no delay. We got the result, or the ships list are highlighted with the blue color immediately, but just the result was not all of the details was not all delivered immediately at the same time. To show you this, yeah, maybe you are noticing here that the scroller is jumping, and that's because the progressive deliver of the items. But you can see it better with the geo field sets, which has over 100 fields. So keep an eye on the scroller. Oh, where is the scroller? So, but, yeah, now. Yeah. Maybe you have noticed it. It's jumping actually, but if I am more quicker than the scroller, I can reach the bottom of the page and can see that the details are still delivered. Each time I'm delivering just 2 details. Okay, the last thing that we can do is actually check the metrics, because there is a change now. Okay. So I will open the performance monitor again and click on the show all. So this time we don't have a large yellow block, but instead of it, we have a jump, then the chart will come back to the bottom, then another jump, and each short jump is reflects that more items are delivered, and the browser was busy with the smaller rendering task. And we will have also a bit similar result on the performance timeline record. So I will start recording. So I will stop it first. Now I start record, then click on the show all. So now I can click on stop again. So we have also a bit similar result to the one we have seen in on the performance monitor. Instead of a large block that was blocking the browser and delaying the time to interactive, So we have more smaller tasks, and the user is not blocked this time. And with this, we have achieved our goal and solved the problem. Okay, before I leave you, I would like to finish the story I have started with. So after committing to solve the problem I have, or the application I have broken in 2019, I started to get better result on Lighthouse. But since that was on my local host, my colleague didn't want to believe it until he see it on the test server. So I worked a bit harder, and a few days later, I have sent him this screenshot from the test server, but he was still not ready to accept that I won the challenge. And his answer was, "This is fake." So I cross my finger to all of you and wish that you can have great performance result that is real and not fake. And with this, we reach maybe a few minutes for Q&A.